Okay, let's start with the fundamental concept of caching. Basically, it's like creating a little memory bank for your application. When you need some data, say an image or product information, instead of always going back to the source, which might be slow, the system first checks if that data is already readily available in its cache. If it is, fantastic. We could serve it up instantly, making things super speedy. But if not, we fetch it from the original location, store a copy in the cache for later use, and then deliver it to you. Okay, let's talk about why caching is so crucial for good app performance. Basically, when a user requests something, it can sometimes take long asterisk time to get that information from the main server, especially if there are lots of other users requesting the same thing at the same time. Caching steps in and says, hold on, I've already grabbed this piece of data for you before. That significantly reduces the delay, making things faster and smoother for everyone. It also takes some pressure off our servers, allowing them to focus on new requests instead of constantly serving old ones. A happy user is a returning user. Caching helps keep them happy. Okay, so when we talk about caching, it's not just one thing, there are several layers. We've got CPU caches right inside your computer's processor, which are super fast for accessing frequently used data. Then you have memory caching, like the RAM in your system, to speed things up even further. This caching uses your hard drive or SSD as a temporary storage spot. For web applications, browser caching is huge. It stores images and scripts locally so pages load faster without constant requests. And don't forget CDN. These distribute content across servers around the world, bringing data closer to users. Finally, databases often employ query caching to avoid running the same complex queries repeatedly. Okay, let's talk about client-side caching. It's a really important concept when you're interviewing for software development roles. Essentially, it means storing data directly on the user's computer or browser. Think of it like this: instead of every time someone visits your website and needs an image or a JavaScript file, they have to download it from the server again. Client-side caching prevents that. It dramatically speeds up loading times, especially for repeat visitors who aren't seeing the initial load. There are two main ways it works: the browser cache, which uses HTTP headers, and service workers, which are more complex JavaScript scripts. Okay, let's talk about server-side caching, a really important concept in web development. Essentially, it's like a quick access storage system for your web server. Instead of always going back to the database or other slower sources when someone requests a page, the server can pull data from its cache if it's already there. There are different types, including browser caching, which is stored on the user's computer CDN that distributes content across servers worldwide; reverse proxy caching, which sits in front of your server; and memory caches like Redis or Memcached, which are super fast because they're in RAM. The key takeaway is to reduce those delays and make websites load much faster for everyone. Okay, let's talk about CDN. Think of them as a global network of super fast servers designed to speed up your website. When someone visits your site, the CDN automatically figures out which server is closest to the visitor and delivers the content from there. A big part of how they do this is caching, storing copies of your static files like images and code on these nearby servers so they don't have to be fetched all the way from your main website every single time. Okay, let's talk about in-memory caching. Basically, it's like having a really quick notepad right inside your computer, specifically the RAM. This means that when you need some data, it's retrieved almost instantly, sometimes even in microsecond time frames. It's **** faster than pulling things from a hard drive or fetching them over a network. Because RAM is temporary though, if the system restarts, all of your cached information will be lost. It's great for things you access often, like user sessions, database queries, and even responses from API, anything that needs to be grabbed super quickly. Okay, so let's talk about distributed caching, a really important concept to know for any performance-focused role. Basically, it's not just one cache sitting on a single server. Instead, we spread the caching across multiple servers, working together. This is crucial because as your application grows and gets more popular, that one single cache can quickly become overloaded and slow down everything. Distributed caching helps us handle all that extra traffic and data without causing performance issues. Think of it like having several backup copies of frequently accessed information, so when someone needs something, they get it faster than if it had to be retrieved from a slower source. Some good examples you might hear about are Redis cluster or memcached when used with techniques like consistent hashing to distribute the data. Okay, let's talk about the caching solutions you've likely worked with. It's really important to know your stuff here. Understanding how different caching layers work is a big plus. We're talking about things like browser caching, where browsers remember static assets locally so they don't have to download them every time. Then there are CDN, which distribute content across the globe for faster delivery. Server-side caching, using tools like Redis or memcached, avoids hitting your database repeatedly. And don't forget database-level caching and object caching, each with its own benefits and considerations. Let's dive into cache invalidation, which is super important for keeping our cache data accurate. Basically, it's about making sure the cache isn't serving up old information. Imagine your cache as a really helpful assistant. Sometimes it makes mistakes and hands out outdated details. To fix this, we need to tell it when something has changed. There are two main ways to do that: time to live, where we set an expiration time for each item in the cache, or invalidation on change, which means we invalidate all cached entries whenever the original data updates. Okay, let's talk about why cache invalidation is such a tricky problem. Think of a really popular website. Its content might be stored in many different caches around the world for speed. But what happens when something changes? If you just tell one cache to throw away the old data, everyone else still has the incorrect information. It's like shouting across a crowded room. Only one person hears your message. The challenge is, how do we make sure everyone gets the latest version of the data consistently, especially in a system where there are many different parts all working together? There are several approaches: write through, write back, and hybrid, each with its own set of trade-offs. Ultimately, it's about finding a balance between keeping things fast available and making sure everything's accurate, consistent. Okay, let's talk about how we make sure our caches are actually accurate. A really important question in any caching interview is, how do you invalidate the data stored in your cache? The most basic approach is TTL, setting an expiration time for each item. It's easy to set up, but be aware that if something changes before the TTL expires, you'll have stale data. Then there's write-through caching, where writes happen immediately to both the cache and the original source. This ensures consistency, but it can slow down writes a bit. Write-back caching is faster for writes because it only records them in the cache initially, with updates happening late. However, you risk losing data if the cache fails before those updates are replicated. Versioned caches store not just the value itself, but also a version number. When data changes, that number changes too, invalidating everything cached. Finally, for more complex scenarios, we can use tags to group related data together so that updating one part automatically clears out the whole group. Okay, let's talk about write-through caching. It's a really straightforward approach to keeping your data consistent. Basically, whenever you save something, whether it's to a database or a file, the change isn't just stored in the cache, it's also immediately written back to where the original information lives. Think of it like updating two places at once. This guarantees that what you see in the cache is always up to date, which is great for consistency. However, because every write operation has to hit both locations, there's a slight performance penalty and it uses more storage space overall. Okay, let's talk about write-back caching. It's a clever technique used to speed up how databases handle writes. Basically, instead of immediately saving changes to the hard drive, they're temporarily held in really fast memory like RAM. Then these changes are written back to disk later, periodically. This means that writes feel much faster, especially when you only have a few updates happening at once. It also helps with reliability because if there's a crash, those changes are already safely stored in memory and can be recovered. Okay, let's talk about write-around caching. It's a bit of an outlier in the world of caching. Imagine you have a frequently accessed piece of data. Instead of keeping a copy around in the cache like with traditional methods, write-around caching means that whenever someone asks for that data, the request goes straight to its original source, the database or API. The server then writes the fresh data directly back into the cache itself. It's like sending the information directly to the destination and having it automatically stored there. This avoids any issues with stale cached content. However, because every single request goes to the origin, you might see a slight increase in latency, and it can put more pressure on your source server. Okay, let's talk about cache-aside, or lazy loading caching. It's a really common technique used in building efficient systems. Basically, it doesn't proactively store copies of your data in the cache. Instead, when someone asks for something, the application checks if that information is already available in the cache first. If it is a cache hit, great, we just serve it right away. But if not, which is a cache miss, then we go grab it from the original source, store it in our cache, and finally deliver it to the user. The lazy loading part means that data isn't fetched unless it's actually requested, saving resources. Okay, let's talk about cache aside and write through two common caching strategies. Cache aside is a really popular choice for applications where you read data frequently but it doesn't change often. The application checks the cache first. If it finds what it needs, great. If not, it fetches it from the original source, stores it in the cache, and then gives it to the user. Now, write through is different. With this method, every time you update something like a product price, that change gets written both to your application ** immediately to the cache. This guarantees that everyone sees the most up-to-date information, but it can slow down your writes a bit. So, when do you use which? Generally, if you mostly just read data and don't need super fast updates, cache aside is your friend. But if strong consistency is absolutely critical, think about things like bank transfers or order processing, then write through might be the better approach. Okay, let's talk about TTL. It's a really important concept in caching. Think of it like an expiration date for your cache data. It's the amount of time a piece of information stays valid in your cache. When something is initially put into the cache, you assign it a TTL that tells the server how long to serve that item directly from the cache before it needs to fetch it again from the original source. It's all about balancing speed and freshness, keeping things fast while still making sure users get up-to-date information. Okay, so let's talk about what happens when a piece of data stored in our cache goes past its due date. Basically, when an item expires, it's considered stale and we need to get fresh information. The first time you request that data after it's expired, it's called a cache miss. Then the application pulls the latest version from wherever it originally came from, our database or API, updates the cache with this new data, and sets a new expiry time for it. There are different ways we can handle expiration too, like using a fixed TTL or sliding window techniques to keep things as fresh as possible. Okay, let's talk about cache eviction policies. They're really important for managing how your cache handles a limited amount of storage. Think of it like this: you only have so much space in your cache, and requests keep coming in. An eviction policy is the rule that says when we run out of room, what do we throw away? There are several common strategies: FIFA, which just removes the oldest items; LRU, which favors recently used data; LFU, which prioritizes frequently accessed information; LIFO for stack-like behavior, less typical; and even a random approach. The best policy really depends on your specific application's needs, how often things change, what you're reading versus writing, and what kind of performance you're aiming for. Okay, let's talk about LRU. LRU stands for least recently used, and it's a really common caching strategy. Basically, it works by keeping track of when each item in your cache was last used. When the cache is full and you need to add something new, you remove the oldest item, the one that hasn't been touched in the longest time. Think of it like a recently visited list on a website. It's great for situations where things you looked at recently are likely to be interesting again soon. Okay, so let's talk about LFU, least frequently used. It's a way of deciding which items to remove from your cache when it's getting full. Basically, the algorithm keeps track of how often each item is accessed. When the cache is at its limit, it kicks out the thing that's been used the least asterisk amount of times. Think of it like this: if item A gets hit 5 times, item B only gets hit twice, and item C just once, then item C would be the first one to go. It's a good strategy for getting rid of rarely accessed data, but keeping track of those frequencies can add some overhead. Okay, let's talk about FIFO. Let's first in, first out. It's a really straightforward way to manage our cache. Think of it like a queue. The data we put in first is the data we take out first. When our cache reaches its limit, the oldest items are removed automatically. It's great for situations where recent requests are more important than older ones, like serving frequently accessed content that doesn't change much. Okay, let's talk about when you'd prefer LRU versus LFU caching. LRU is pretty straightforward. It kicks out the data that hasn't been touched in a while. Think of it like this: if you're working on a project and just finished a chapter, you'll probably revisit those notes soon. That's the temporal locality principle LRU leverages. It's great when you need quick access to frequently used things but can handle occasional misses. Now, LFU is different. It evicts items that have been accessed the least often. This works well if your data has a really diverse mix. Some items might be hot and popular, while others are rarely touched. LFU helps you keep less important items off your memory, even if they're currently trending. Okay, let's talk about a really important issue in caching: cache stampedes. Imagine a huge wave of users all trying to access the same piece of content at once. This can overwhelm your cache and force every single request to go straight to the origin server, leading to slow speeds and potential problems. It happens when something suddenly becomes super popular, maybe because of a viral post or breaking news. To prevent this, you need to be smart about how you invalidate your cache. That means removing old content when it changes. Also, consider techniques like tokenization, where each user gets a limited ticket to access the resource, preventing multiple simultaneous requests. And finally, rate limiting and queuing can help manage the flow of traffic and keep things running smoothly. Okay, let's talk about cache warming. It's a really important concept when discussing caching strategies, especially in interviews. Basically, it means proactively filling your cache with data before users actually ask for it. Think of it like making sure your car engine is warm before you drive off. Without doing this, the first time someone requests something cache, there can be a noticeable delay, which isn't great for user experience. It's about anticipating those common requests and getting the data ready to go. You might fetch the data from your database or API and put it in the cache, or you could schedule a background process to keep refreshing it periodically with new information. Okay, let's talk about a common challenge in caching called the hotkey problem. It basically happens when you have one piece of data. We'll call it a hotkey that gets access to more often than anything else. Because of this high demand, the cache might get filled up with just that single item, leaving little room for other requests. This means those other requests could be delayed, and in some caching systems, repeatedly serving the same hotkey can actually cost more money, especially if the cache uses expensive memory. It's like having a supermarket only stocked with chocolate. You get your chocolate fast, but everything else takes longer to find. Okay, so let's talk about the really common problem when using distributed caches: hotkeys. Think of it like this: you have a key that gets access to way more often than other keys. This can cause some serious issues. First, you might experience something called a cache stampede, or the thundering herd effect. That happens because multiple requests for the same key all hit the same cache node at once. The node then has to go fetch that data from its slow backend like a database, and everyone else waits. It creates performance bottlenecks. Also, some nodes can end up handling those requests for one particular hotkey, which leads to an uneven workload. To combat this, we use a few techniques: probabilistic early expiration, where we gently expire keys that haven't been used in a while, even if they're still valid; distributed locking, so only one node gets the data at a time; sticky sessions, directing users to the same cache node whenever possible. We also use consistent hashing for better key distribution and sometimes prefetch the data for frequently accessed keys. Okay, let's talk about consistency in caching. You'll often hear the term strong consistency and eventual consistency. Strong consistency basically means that if you update something in your cache, every one asterisk instantly asterisk sees the change like a real-time reflection of truth. But achieving this can be tricky and slow down performance significantly. On the flip side, eventual consistency says the data will eventually become consistent across all copies, but it might take a little while. Think of it like updates slowly spreading out on social media. It's simpler to implement and offers better availability, even if there's a slight delay in seeing those changes. Okay, let's talk about cache sharding. Basically, it's like breaking up your cache into smaller pieces and spreading them out across multiple caches. Imagine you have a huge amount of data. Instead of cramming everything into one big cache, you divide it up and store each chunk in its own separate cache. This makes things much more scalable, so you can handle more requests and more data without slowing down. And if one of those smaller caches goes down, the rest of your system keeps running smoothly. That's a major benefit for resilience. Okay, so let's talk about what happens when your application tries to find something in its cache and can't. That's a cache miss. It's basically like looking for a book on a shelf and realizing it isn't there. When this happens, the system needs to go back to the slower source of truth, usually a database or some other external API, to get the data. After fetching it, we immediately put that data in the cache so the next time someone asks for it, it's readily available. It's all about minimizing those misses and keeping things snappy. To really tackle these misses, you can think about increasing your cache size, using strategies like least recently used to prioritize what gets kept, or even optimizing how the data is prepared to fit nicely into the cache. Okay, let's talk about cache hit ratios. They're super important for understanding how well your caching is actually working. Essentially, it tells you what percentage of times the user gets their data directly from the cache instead of having to go all the way back to the original source. It's calculated by dividing the number of successful cache hits by the total number of requests. For instance, if you get 100 requests and 80 of them come straight from the cache, your hit ratio is a healthy 80%. A high hit ratio means users are getting their data really quickly, reducing stress on your servers, saving money on infrastructure. It's a win-win-win. But remember that the size of your cache and how you keep it up to date play a big role in achieving those good numbers. Okay, let's talk about monitoring your caching systems in a production environment. It's absolutely vital. You wouldn't want performance problems hiding in the shadows. We need to keep a close eye on a few key things. First, we check the hit rate, which tells us how often we're actually serving content from the cache instead of going back to the origin server. Next, we look at cache misses. Understanding why this happen is super important for optimizing our caching strategy. We also need to monitor latency, how long it takes to get a response. And, importantly, we keep tabs on how full the cache is. Too much and things start slowing down. Finally, let's not forget about errors. Anything unusual here should be investigated immediately. Tools like Grafana or Prometheus are great for visualizing this data, and setting up alerts can help you catch issues before they impact your users. Okay, let's talk about content-based caching, a really important concept for any performance optimization discussion. Essentially, it's not just about remembering what something is but also recognizing if we've seen something similar before. Instead of relying solely on the URL or ID to find cache data, the system actually analyzes the content itself. It's like having a super smart memory that can compare requests and pull in the closest match. This leads to much faster loading times and reduces the strain on your servers. It's a win-win. Okay, let's start with HTTP caching. It's absolutely fundamental to understanding how websites load quickly. Basically, it's like a website giving its resources a little memory so they don't have to be downloaded every single time you visit. The browser and servers themselves can both cache things. The browser stores files locally, so the next time you go back to a site, it doesn't need to download them again. We use headers like cache control and expires to tell the browser how long to keep something cached. or to let it know if it needs to be refreshed. And we also have e-tags, which are basically unique fingerprints for resources. They help browsers determine if a resource has changed since it was last cached. Okay, let's talk about how we tell browsers and other caches to remember things or not. The most important header here is cache control. It's like a set of instructions. Max age tells the cache for how long it can hold something. Smaxage is similar but specifically for shared caches, like CDN. Public means anyone can use the cached version, while private means only your browser should use it. Then we have no cache and no store, which tell the cache to asterisk not asterisk use the resource at all. Older headers like expires are still around, but cache control is generally preferred now. And finally, e-tag and last modified help verify if a cached copy is still current. Okay, let's talk about e-tags. They're a really clever way to make caching even more efficient. Basically, an e-tag is like a unique fingerprint for a specific version of a resource assigned by the server. When you first request something, the server sends it back asterisk with asterisk that fingerprint. You then store that fingerprint locally in your browser or application cache. The next time you ask for the same thing, you send over your stored e-tag. If the server sees that e-tag matches what it has, it knows the resource hasn't changed and just sends back a 304 not modified response, meaning you can use your cached version. This avoids wasting bandwidth and transferring the entire file again. If there asterisk has asterisk been an update, the server sends the new version with a new v-tag and you refresh your cache. Okay, let's talk about stale while revalidate. It's a really important caching technique to understand. The basic idea is that when you request something, the browser first checks its local cache. If it has an older version, it immediately serves asterisk the asterisk that's the stale part. But, importantly, while it's doing that, it quietly fetches the latest version from the server and updates its cache in the background. It's all about speed for the user, and eventually getting them fresh content, so you don't have to wait around for every single request. Okay, let's talk about negative caching. It's a bit of an odd concept, but it's really useful in specific situations. Think of it as intentionally serving an old version of something like an image or piece of data to give you instant gratification and speed up the initial response. Essentially, it tells the cache, hey, this is out of date, don't bother checking for a new one just yet. It's especially popular with CDN because they can quickly deliver that old version while waiting for the origin server to update its content. It ensures you always have something to show the user, even if it's not perfectly current. Okay, so caching is great for speeding things up, but it's not a magic bullet. There are definitely times when you should hold off on using it. If your data changes really often, like constantly updating stock prices or user profiles that get tweaked all the time, then caching could actually give you outdated information. Similarly, if you're doing something really heavy duty in terms of processing power, like a complex calculation, don't cache that. It might take longer to get the result from the cache than it would just do it directly. And if users need very specific, tailored results, caching can cause everyone to see the same thing. Finally, be super careful with data where accuracy is absolutely critical, things like financial transactions or medical records. You simply can't risk relying on a cached version that might not be completely up to date. Let's talk about making smart choices when it comes to caching. It's not enough to just grab any data and put it in a cache. You need to think carefully. Start by looking at how people are accessing your information, what's being used most often. Then consider how quickly that data is changing. If something changes constantly, a cache might actually make things worse. Think about the consequences of serving outdated info too. Could it cause problems for users or your business? Finally, don't forget to factor in resource constraints like storage space and processing power. Prioritize caching what delivers the most value without overspending. Okay, let's talk about a really important aspect of caching: the risks involved when we're dealing with sensitive information or data that changes quickly. Caching is awesome for speed, but if you don't think about it carefully, you could introduce some serious problems. One major risk is security. A compromised cache means an attacker potentially has access to private details. Another thing to watch out for is data staleness, basically using outdated information, which can lead to really bad decisions. And of course, regulations like GDPR and HIPAA have strict rules about how we handle personal data, so caching without proper safeguards could be a violation. Finally, there's the threat of cache poisoning, where someone deliberately injects incorrect data into your cache. So, when you're planning your caching strategy, especially for important systems, always keep security and freshness top of mind. Okay, let's talk about handling concurrency when we're dealing with caching. Think of it like this: multiple users trying to update the same piece of information at exactly the same time. That's a race condition and can lead to some seriously messed up data. There are several ways to tackle this. You could use locking mechanisms, essentially making sure only one user can change something at once. Or you might try an optimistic approach, checking if the data has been updated since you last read it before trying to write it back. Transactional caching is another option, where all the changes happen as a single unit. And finally, sometimes we're okay with slightly delayed updates. Eventual consistency can be a great strategy for scalability, especially when strict accuracy isn't essential. Okay, let's talk about how distributed caches handle replication. Think of a big library. Instead of keeping all the books in one place, we split them up and put copies in different branches. That's essentially what's happening with shards. Each shard is like a section of our data spread across multiple servers. Now, for each section shard, there are several copies replicas. If one server goes down, the others can still serve the data. We use something called consistent hashing to make sure keys get routed to the right replicas, and that when a key moves, only the relevant copies need updating. And sometimes we use quorum-based replication, where a group of servers collectively decide which copies are authoritative, ensuring consistency even with failures. Remember, there's often an eventual consistency model in place. Data will eventually be consistent across all replicas, but it might not be instantly so. During the interview, be prepared to discuss how you'd handle conflicts and what level of consistency is appropriate for your application. Okay, let's talk about what tools you might use for caching in your tech stack. On the front-end side, with JavaScript, BarStack is a good lightweight option for static assets, while service workers are fantastic if you need to handle offline functionality. And don't forget Vercel's edge functions and Next.js image optimization. They really streamline the process. Moving to the back-end, Redis and Memcached are consistently popular choices due to their speed. They are great for things like session management and rate limiting. You'll also find tools like CacheStore for Node.js and Flask caching, or Django's cache framework if you're working with those languages. It's all about picking the right tool for the job, keeping scalability and ease of integration in mind. Okay, let's talk about caching in the context of microservices. Microservices are fantastic for flexibility, but sometimes all those calls between services can add up to noticeable latency. That's where caching comes in. We need to think carefully about where caching data may be at the edge with a CDN within a specific service, or using a distributed cache like Redis. Data consistency is really important too. You'll want a strategy for keeping your cached information up to date and avoiding problems when things change. There are several common patterns you can use, like caching specific routes, utilizing HTTP headers to control how browsers handle caching, or even using service mesh features if you have them. The right approach depends on the particular services in your architecture. Okay, let's talk about multi-level caching. It's all about layering your approach to storing frequently accessed data. Imagine it like a set of filters. The closer you are to the user, like the browser cache, the faster the response. We start with the browser itself, which stores static assets like images and CSS. Then we move on to CDN, distributing content globally for speed. After that, a reverse proxy, such as Varnish, sits in front of our application server, caching frequently requested dynamic pages. Finally, we have an in-memory cache from the server itself, things like database queries or session data, which is super fast but has limited space. Okay, let's talk about cache loaders. Essentially, a cache loader is like the go-between for your application's cache and the places where your actual data lives, often databases or external API. Its job is to grab the latest information from those sources, format it if needed, and then load it into the cache so that subsequent requests can be served much faster. It's a crucial part of keeping things speedy. They're responsible for getting the initial data, handling any potential issues like errors during retrieval, and most importantly, putting that fresh information into your cache. Okay, let's talk about hybrid caching. Think of it like a layered approach to storing things, like a multi-layered cake. We're not just relying on one type of cache, we combine several. A CDN is your first line of defense, bringing static content closer to the user. Then there's the browser cache, the user's own computer holding copies. And finally, we have server-side caching, storing data right on our servers for super fast access. It's a clever way to make sure everything loads quickly and efficiently by using the best tool for each job. Okay, let's talk about read-through caches. Think of it like this: you ask for something, we fetch it from its original location, maybe a database ***, immediately copy that entire thing into our superfast cache. So, the next time someone asks for the same data, it's already there waiting. It's great for speeding things up when you get hit with lots of reads but not so much writing. It means every request triggers a copy to the cache, which can add some write load on your main system. Thank you for watching.